From Calculus 1, you should remember a little bit about maximums and minimums and how we find them just with functions of one variable. As we jump to functions of two variables and we're looking at surfaces and we want to find maximums and minimums, since our function is going to be a function of two variables, we're going to have z equals f of xy. And if you remember in Calculus 1, the way we found maximums and minimums were first by finding critical points. So there is a very similar way with functions of two variables for finding critical points, except it involves both of our input variables, which are x and y. One other problem we run into is in Calculus 1, we're looking for where the derivative is 0 or undefined. Now with functions of more than one variable, we don't have anything that's specifically called the derivative. What we have now are partial derivatives. So the point AB is the location of a critical point if one of the following is true. The first one is our three-dimensional equivalent to the derivative being 0, but since we have partial derivatives instead of just a derivative in functions of two variables, we have to have both partial derivatives equal 0. So we're going to say f sub x at AB equals 0 and f sub y at AB equals 0. So anywhere where both of the partial derivatives are simultaneously equal to 0 will be a critical point. From Calculus 1, we also said anywhere the derivative is undefined, we would have a critical point. So for this one, it's an or. So f sub x at AB or f sub y at AB is undefined. And undefined doesn't really tell us a whole lot. It could be that the graph comes to a sharp point, which means it would not be differentiable. We could have like a cliff, which is a place where the limit doesn't exist, so it would not be differentiable there either. So it's very similar criteria to Calculus 1. The only jump we need to make is to involve partial derivatives instead of just the derivative. So we're going to try to find all critical points of the function f of xy equals x squared minus 2xy squared plus x minus 3. We want to find all the critical points. Now, we haven't talked yet about whether they're going to be maximums or minimums, but before we can do that, we have to be able to first locate these critical points, which are the points that we need to investigate further. So all of our criteria for critical points involved our partial derivatives. So the first thing you should do is find your partial derivatives. So f sub x is the partial with respect to x. We get 2x minus 2y squared plus 1. And then f sub y is the partial derivative with respect to y. And we get negative 4xy. Now we want to know where either of these is equal to 0 or undefined. Well, they're both polynomials, so they're never going to be undefined. So we don't have to worry about that second criteria. So neither will ever be undefined, and that's because they're the way that they look, they're polynomials. Remember, undefined is when we are dividing by 0 or taking the square root of a negative, things like that. So the only other option is that our critical point is a place where both of them equal 0. So negative 4xy equals 0 and 2x minus 2y squared plus 1 equals 0. So negative 4xy could equal 0 if either x equals 0 or y equals 0. So we've got two things we need to look at. So option number 1, if x is equal to 0 in my second equation to satisfy this criteria, I'm going to plug in x equals 0. What I'm left with is negative 2y squared plus 1 equals 0. And we're going to solve that for y. So we'll get 2y squared equals 1. So y squared is a half, which means y equals plus or minus the square root of that, and I'm just going to rationalize it, square root 2 over 2. So that gives me 2 potential points so far, 2 critical points. One of them is at x equals 0, y equals positive radical 2 over 2, and the other one is at x equals 0, y equals negative radical 2 over 2. Now the other option to make our first equation equal 0 is that y is 0. So if y equals 0 in this equation, we're going to be left with 2x plus 1 equals 0. And when we solve that, we get x equals a negative half. So we have a third critical point now, negative 1/2, comma 0. So those are our 3 critical points. All 3 of those points would make both f sub x and f sub y equal 0. And we can plug that back in to check if you want to. Now to actually decide what is happening in terms of maximums and minimums at these critical points, we are going to use something that's very similar to the second derivative test from Calc 1. And here in Calc 3, it's still called the second derivative test. The only difference now, again, is that we're dealing with partial derivatives. And there are technically 4 second partial derivatives. So all of them are going to be involved slightly with this test. Now, the second derivative test in Calculus 1 tests the concavity at each of our critical points. And if you remember, if I had a parabola and I determined that this was a critical point, all I needed to do was test the concavity at that point. And if it was concave down, like this one is, that means we have a max. If it's concave up and we have a critical point, that means we have a min. Now what changes slightly here in Calculus 3 is we've got second derivatives in several directions. So we actually need to check to make sure that the same exact thing is happening in both the x direction and the y directions. Otherwise we produce what's called a saddle point. And a saddle point is the point that's in the center of those hyperbolic paraboloids, where if you look at it from one perspective it looks like a max, but if you just turn it slightly, look at it from a different perspective, it looks like a min. So all of this information is compacted down into just a little formula that you can check. Suppose that the second partial derivatives of f are continuous throughout an open disk centered at the point AB. So B is our critical value that we are trying to analyze. So this phrase might seem kind of odd, but all this is guaranteeing is that we're dealing with an area of the graph that is continuous and differentiable, which is useful because sometimes we want to evaluate rational functions or square root functions. Even though we know that they have problem spots, we just need to avoid the problem spots. We can really analyze everything else on the graph. We just need to avoid the problem spots. So even if f does have a problem spot, what we're guaranteeing here is that we're looking in a little area that doesn't contain any problem spots. We're looking in an area where the graph is continuous and differentiable. We're going to be calculating something that I've always learned is called the discriminant, although our textbook doesn't exactly call it that, at least not here in the definition. And this discriminant is calculated by taking your second partial with respect to x at your critical value, multiplied by your second partial with respect to y at the critical value, and then subtracting your second mixed partial derivative at the critical value squared. And the reason we're squaring this last one is, if you remember a few sections ago, we said if we're dealing with a piece of a surface that's continuous, then our mixed partial derivatives will be equal. So squaring f of xy is the same thing as multiplying f sub xy with f sub yx. So it just reduces one extra thing that we need to calculate. So depending on what this value comes out to be, it will tell us what exactly is going on at this critical point. So if the d value comes out to be positive, and the only way that could possibly happen is if your f sub xx and f sub yy have the same sign. They're either both positive or both negative. Then the product will always be positive. And then we're going to subtract off f sub xy squared. And then if d came out positive, that means our concavity in the x and y directions are the same, and they far outweigh what's happening here when we combine the x and y directions. So if the d value comes out positive and f sub, let me change colors, f sub xx is positive. Remember we said a little bit earlier, second derivative tells us concavity, and if concavity is positive, that means it's concave up and we have a minimum. So the d greater than 0 is just telling us that our concavities are in agreement. If we look in the x direction and if we look in the y direction, they're doing the same thing, which boils down to the fact that we do not have a saddle point. So if the d is positive and f sub xx is positive, then AB is a relative minimum. Now it could be a global minimum or an absolute minimum, but we will talk about those, any extra criteria for those in a few minutes. The other option also has D being positive, which means our concavities are in agreement, but this time f sub xx is negative, which means concave down. And since the D is positive, it's not only concave down in the x direction, it's also concave down in the y direction. Then AB is a relative maximum. If D comes out to be negative, what that tells me is my concavity in my x and my y directions do not match, which means I can look at this surface from one perspective and it looks concave down, but then when I turn it slightly and look at it from a different perspective, it looks concave up. And what we call those are saddle points. And it doesn't matter which direction is concave down, concave up, so there's no extra stipulation on f sub xx or f sub yy. And remember, a saddle point, and you might want to look back at this graph, is that center point on a hyperbolic paraboloid that we talked about in class, where in one direction it looks like we have a concave up parabola, but then if we spin it 90 degrees, in another direction, it looks like we have a concave down parabola, and they meet right at their vertices. And there's always the dreaded inconclusive. Remember in Calculus 2, when we did all of our series tests, that could be a possibility. So if D comes out to be 0, then the test is inconclusive. So we're going to revisit the example we just did above, and we're going to test those 3 critical points and try to decide what's happening at each of them. So we're going to test the previous 3 critical points to determine if any are relative extrema. So that's just a shorter way of saying maximums or minimums. So we're going to need a bunch of this information from before. So our function was x squared minus 2xy squared plus x minus 3. And I'm not sure I copied that right. Let me check one more time. X squared minus 2xy squared plus x minus 3. So I got a couple of signs wrong. We also need our list of critical points, because we're actually going to be plugging them into that D formula. So when x was 0, we said that the y had to be negative radical 2 over 2 or positive radical 2 over 2. And when the y was 0, I believe we said x was negative 1/2. And those 3 points would make both our partial with respect to x and our partial with respect to y equal 0 at the same time. Yep, it was negative 1/2. So the first thing we need to do is calculate all our derivatives here. So f sub x, we've done these already. I'm just going to write them again real quick. F sub x is 2x minus 2y squared plus 1, which means f sub xx is 2. F sub xy is negative 4y. f sub y is negative 4xy. F sub yy is negative 4x. So remember, we don't need f sub yx, although in this case, I may have made a mistake. Hold on just a second. It should be true that f sub xy and f sub yx would be exactly the same, and they would be. So f sub yx, if you look back right here, if we came back and did the derivative with respect to x, it would be negative 4y, which is the same thing we got here. So d is f sub xx times f sub yy minus f sub xy squared. I'm going to simplify that just a little bit, and then we will plug in our 3 points to see what's happening. So we've got negative 8x, and that's going to be minus 16y squared. So we've got to test the value of d at each of our critical values. So one of the critical values was x equals 0, y equals negative radical 2 over 2. So we plug that into this d formula we just found. We've got negative 8 times 0 minus 16 times negative radical 2 over 2 squared. Well, this guy's just 0. And if I square negative radical 2 over 2, I get 2 over 4, which is a half. So I've got negative 16 times a half, which is negative 8. D came out negative, which means this is a saddle point. We'll go ahead and test our next critical value, which just changes the sign of the y coordinate, which is going to give us the exact same thing because the y ends up getting squared, so the negative doesn't really matter. We have negative 8 times 0 minus 16 times radical 2 over 2 squared. So that's 0. We get negative 16 times a half, which is negative 8. Our d value came out negative, our discriminant, so again we've got another saddle point. Which is pretty interesting that we've got 2 saddle points on this graph. Our last critical value we're going to check is x equals negative 1/2, y equals 0. So we get negative 8 times negative 1/2 minus 16 times 0 squared. So now the second term is 0. And we've got a negative times a negative in front, which is a positive 4. Perfect. So our d came out positive, which means we do have a maximum or a minimum, and it's going to depend on the concavity in the x and y directions. And by d being positive, we've already proved that the concavity in the x and y directions will be in agreement, so we really just need to look at one of them. And I'm going to look at xx because it's the simplest. So f sub xx equals 2, which is positive, which means concave up. And if it's concave up, that means we have a minimum at negative 1/2, 0. Now this might backfire on me, but I want to try and graph this thing. I'm going to go to Wolfram Alpha and try to graph this thing real quick and see what's happening. So there's our function. And we've got x squared minus 2 times x times y squared plus x minus 3. And they give us a little contour plot, which sometimes is helpful. And unfortunately, Wolfram Alpha doesn't let me manipulate this. But in the y direction, notice we're only going to like positive negative a half, which I think we need to be going a little bit further to see our saddle points. But it does show, if you look here, that when x is, and what did we find? When x was negative 1/2, y was 0, we should have a min. So that one's not showing in our range either. But you can see definitely at y equals 0, there is like a low spot that extends in both directions. And the way that Wolfram Alpha works is it colors deeper and deeper as the values get smaller and smaller. So it looks like this is not just a smooth continuous like parabola where that bottom trough there all has the same value. It looks like it's getting deeper and deeper and deeper as we go towards y equals 0. So if we imagine continuing along this line, this x value to negative 1/2, it does at least go down, and we found that it was a minimum, so that's helpful. So I thought that might blow up in my face. It kind of did. So we weren't actually able to see the points that we needed. But it did make sense that when y was 0, there was something going on the graph. So these are just relative maximums and minimums, which are like the top of a hill or the bottom of a valley. It doesn't necessarily guarantee that it's going to be the largest value on the graph or the smallest value on the graph. Those are called either global extrema or absolute extrema. Just to give you a two-dimensional example, if I wanted to find the absolute extrema on this graph, technically this graph goes up forever to infinity and down forever to negative infinity. So really is no absolute max and min. And what we learned in Calculus 1 is that if we specify a closed interval on this graph, so we just look at the piece between the dots, then we will have a absolute extrema. So if you define a continuous function on a closed interval, then you will always get an absolute max and an absolute min. You are not guaranteed to find an absolute max and min on an open interval, and that's because the absolute extrema might be the endpoints, and with an open interval we don't include the endpoints. So this is just paraphrasing here from something we learned in Calc 1, but a continuous function on a closed interval will always have an absolute maximum and an absolute minimum. The only adjustment we need to make to find these is that point could certainly be at a critical value, which we've learned how to do, but it could also be at the endpoints. So we need to include the endpoints in our analysis. Well, the trouble we come in that comes up in 3 dimensions is that there's no specific endpoint because our independent variables form a 2-dimensional grid. So really, we're going to be defining like a two-dimensional area to look in. So it's not going to be endpoints that we check, but it's going to be boundaries. So to find absolute extrema on, let's say, a closed region, what we're going to do is we're going to compare the output values, because absolute extrema means the absolute highest point and the absolute lowest point. So the only way for us to be certain about that is to actually check what those values are, the z-values. So to find absolute extrema on a closed region, we are going to check the functional values at all critical points within the region, all boundaries of the region, and then if it's rectangular, we're also going to check the corners of the region. And we are going to continue this in the next video. We will talk about finding absolute extrema on a closed region.